Alright class, so this is an ALEKS topic that's called using the Nernst equation to calculate non-standard cell potential. And the first thing that we need to sort of do or figure out is what the Nernst equation is. So I'm going to write that down up here for you, and if you look on your equation sheet, you should find this equation. So E equals E naught, so that's the standard potential, minus RT over NF natural log of Q. So this is the Nernst equation, and it will allow us to calculate the potential from non-standard sort of conditions. So normally when we think about our standard conditions, we're looking at a table like this. We've got all of our cell potentials. This is our standard state cell potentials. This is all for 1 molar solutions. This is what we're talking about. So in this equation here, this problem here, we're going to be using concentrations that aren't exactly 1 molar. So that's when we would use the Nernst equation, is when we see these concentrations that aren't exactly 1 molar. So in this case, what we're going to do is we're going to sort of combine that information and this equation in order to calculate the potential when I'm not at standard state. So the first thing, there's a number of things that need to happen in a problem like this. The first thing that I might do is I might break this overall redox reaction down into the two half reactions. So the two half reactions would be, starting at this side, MnO2 solid plus 4H plus aqueous plus 2 electrons goes to Mn2 plus aqueous plus 2 H2O liquid. Now, you might be a little bit confused about how I came up with this is the half reaction. And really what I did is I basically looked up in my ALEKS data tab for a reaction that had MnO2 and 4H plus, going to Mn2 plus, had parts of this reaction that I could then sort of match up, essentially. So I'm just looking at my ALEKS data tab and matching up. I found this equation, and this equation has a reduction potential equal to 1.23 volts. So that is my reduction potential for this reaction, this half reaction, and I know that this is a reduction, it's gaining electrons. I got the electrons on the left hand side, so this is my reduction reaction. And then for the other part, the chromium, I would have a half reaction of 2Cr2 plus goes to 2Cr3 plus, again plus 2 electrons. So I'm writing this off of here. When I look up the reduction potential for this, it's going to be the opposite, right? They're all written as reduction. So what I'm looking for in my ALEKS data tab would be Cr3 plus 1 electron goes to Cr2 plus, and the potential for that. So the reduction potential is minus 0.41. So for this reaction as it's written would be a positive 0.41 written as an oxidation, or excuse me, yeah, written as an oxidation. Got to make sure that we should just write oil rig down, right? Oil rig, so we remember, keep it straight in our minds. So from this information, I can calculate the E naught for this cell. So for this cell, as it's written, the standard state potential would be 1.64 volts. So that would be my E naught, my standard state. And that's actually what's going to go into my Nernst equation here as E naught. Now the other things that we need to the other part of this that we need to consider is what this Q value represents. So for this given equation here, the Q value is going to equal, just like we would do in normal Kc or equilibrium, is going to equal my concentration of Mn2 plus times my concentration of Cr3 plus squared. So I'm leaving out the water because it's a pure liquid. It would not show up in our equilibrium constant. So Mn2 plus concentration, Cr3 plus squared over, so that's my products, over my reactants. This MnO2 is a solid, so we leave that out. H plus would be next to the 4th power, and then Cr2 plus squared. And so this is how I'm going to calculate Q using these non-standard concentrations that are given to me. So everywhere, so I've got 3.17 molar Mn2 plus, that's going to get plugged in here, so on and so forth. So if I write that out, 3.17 times 7.75 squared over 2.80 to the 4th power, and then 5.01 squared. And if I do that calculation, you end up with a Q value equal 0.12 sort of convenient there. So that is my Q value for this non-standard state, non-standard cell that I'm sort of setting up. So now I've got sort of all the pieces I need to use my Nernst equation. So my Nernst equation, the potential that I'm going to plug in as my answer is going to equal 1.64 my E naught minus R, which is 8.314, so that's going to be the R value from your equation sheet, times the temperature in Kelvin, obviously, so 298, so 25 degrees Celsius right here, 298 Kelvin, divided by N. So now N is going to be the number of electrons that are passed back and forth in my balanced redox reaction. So in this balanced redox reaction, this is a nice reason why it's good to write out our half reactions. There's 2 electrons being passed back and forth. So that 2 is going to be my number of electrons. So I'll just put a 2 in there. And this is going to be based off of your balanced chemical equation, your balanced redox equation. Now, you might have sort of skipped over. When we looked up this value for CR2 3 plus going to CR2 plus on our ALEKS data tab, that is just, it says 1 CR2 plus 1 CR3 plus 1 electron. If I double this, the potential stays the same, right? I'm going to change the sign when I flip it from redox or reduction to oxidation, but if I'm just multiplying by 2, then this number stays the same, but this 2 electrons, that's going to be what gets passed back and forth. That becomes my 2 down here. And then F, the value of F is 96,500. That's again a constant on your data sheet. And then the natural log of Q, which is 0.1234. So this is how we'd use the Nernst equation. We'd do this calculation, and if you do this, you end up with E value equal to 1.67 volts. So this is going to be in volts, and that's what I'm going to plug in here as my answer. That's my final answer, 1.67 volts. So it changes a little bit, right? This is my standard state potential. This is my potential under non-standard conditions. So that's just basically how it's done. So just a quick recap. Starting from the Nernst equation, so this is an equation that is on your equation sheet for your final. We can remember oil rig. I'm going to write out my half reactions for this redox reaction, so each half reaction, and I'm going to use my ALEKS data tab to sort of help me figure out what those relevant half reactions are. The number of electrons here, I want to make sure that they're the same because it's got to be a balanced chemical equation. And that number of electrons, whatever shows up in my half reactions, that's going to be what I plug in as the N value in my Nernst equation. So that's going to be my number of electrons. I can calculate my standard state. So this is just going to be adding this together, 1.23 plus this 0.41. That's going to give me my standard state potential of 1.64. Once I have that, then I'm going to calculate Q. I'm going to calculate Q just like I would calculate for any equilibrium type reaction. This is all related, right? So calculate Q, my products over my reactants. I'm going to leave out my liquids and my solids, get this Q value, and then basically it's just plug everything in. So at the bottom here, I'm just plugging everything in. This is my E naught minus my R value, equation sheet, temperature, number of electrons, like I said earlier, Faraday's constant, F value, natural log of Q, and you should get this value of 1.64 volts. So make sure you use the right number of sig figs and put in that V for volts.